Picture this. 2 million years ago, an extraordinary species dominated our planet. These weren't modern humans like ourselves, but rather an ancient lineage that would flourish for nearly 20 times longer than our entire existence. This isn't merely another prehistoric tale. This represents the greatest success story of human endurance and adaptation ever documented. Allow me to introduce you to Homo erectus, literally the most triumphant human species our world has ever witnessed. If you happen to be using this content to drift off to sleep, that's exactly why I create these videos. Consider subscribing and sharing your location and current time in the comments. I love reading them and discovering this incredible global community where someone might be having breakfast in Berlin while another person winds down for bedtime in Boston, all experiencing this journey together. What transforms their existence into something truly extraordinary? They managed to inhabit our planet for an absolutely staggering 2 million years. 2 million! That's such an incomprehensible time frame that our minds can barely grasp its magnitude. To put this in perspective, our own species, Homo sapiens, has merely existed for roughly 300,000 years, making us practically newcomers in the grand evolutionary timeline. Meanwhile, Homo erectus, these remarkable ancient humans, ruled Earth's diverse landscapes spanning 3 entire continents for such an extended period that our complete species history appears like a mere moment in comparison. I'm about to guide you through an incredible temporal expedition where you'll uncover how these prehistoric humans survived, their physical characteristics, their cognitive abilities, and most importantly, why they're absolutely crucial to comprehending what defines humanity itself. You'll learn why numerous scientists regard Homo erectus as the first genuine humans in our evolutionary narrative, a species sharing more similarities with us than any creature that preceded them. They possessed human-like appearances, moved with familiar gaits, and most likely communicated using methods remarkably comparable to our own. Here's something that will absolutely blow your mind. These weren't simply primitive cavemen fumbling around with the rudimentary implements. Recent archaeological breakthroughs have unveiled their astonishingly sophisticated abilities, ranging from creating complex stone tools to constructing elaborate shelters, and even demonstrating clear evidence of compassionately caring for their elderly and vulnerable community members. Their extraordinary resilience while navigating 2 million years of dramatic environmental shifts and deadly predators literally established the groundwork for our modern existence. Let's examine their phenomenal timeline more closely. Homo erectus initially emerged approximately 2 million years ago and persisted until surprisingly recent times, around 100,000 years ago. That's correct. The final populations of Homo erectus were still flourishing on Earth precisely when our own species began expanding across the globe. The most recent known Homo erectus fossils originate from Nandong, located on Java Island in Indonesia, where archaeologists uncovered a dozen skull fragments and 2 leg bones dating approximately 108 to 117,000 years ago. This discovery naturally sparks an absolutely captivating question. Could Homo erectus and Homo sapiens have actually encountered each other? Did our direct evolutionary ancestors ever cross paths with these ancient humans who had ruled the planet for such an extensive period before us? It's an incredibly intriguing possibility that researchers have been exploring for decades. We understand that Homo sapiens departed Africa for Europe and Asia roughly 90,000 years ago. However, that timeline continues getting revised backward with each new discovery. A Homo sapiens fossil discovered at Mislia Cave in Israel dates between 177,000 and 94,000 years ago, indicating we left Africa much earlier than previously believed. But here's where everything becomes fascinating. The earliest evidence of Homo sapiens on Java, where Homo erectus made their final stand, dates between 60 and 70,000 years ago. Unfortunately, this suggests Homo erectus didn't survive long enough on Java to encounter modern humans. Furthermore, no fossil evidence anywhere globally conclusively demonstrates direct interactions between erectus and contemporary humans. However, there's an absolutely unexpected plot twist emerging from the most unlikely source imaginable. Head lice. Yes, you heard correctly. According to research published in the Public Library of Science Biology, Human head lice actually originate from two ancient lineages that separated about 1.9 million years ago, during Homo erectus's prime, but long before modern Homo sapiens existed. One lineage of these parasites exists worldwide and experienced a population decline around 100,000 years ago, perfectly aligning with modern human expansion. But the other lineage, found exclusively in the Americas, has remained completely separate for the entire 1.18 million years. This split between lineage groups corresponds with early human species divergences, suggesting they evolved alongside different human populations. If these lice genuinely evolved with Homo erectus 118 million years ago, then the fact that modern humans carry them implies a direct transfer must have occurred, requiring physical contact between Homo erectus and early Homo sapiens. Since no fossil evidence supports direct interactions, scientists remain highly skeptical. This lice evidence presents one of many captivating mysteries surrounding these ancient humans that researchers continue investigating. The initial Homo erectus fossils were uncovered in 1891 by Dutch researcher Eugène Dubois. After years of searching Indonesia for what contemporary scientists called the missing evolutionary link between apes and humans, Dubois discovered a remarkably preserved skull fragment at Trinil on Java's Solo River. The specimen featured pronounced brow ridges, a sloping forehead, and an angled posterior skull, characteristics that Dubois claimed represented the evolutionary connection between apes and modern humans. Other scientists initially rejected his interpretation, but Dubois was eventually proven correct when similar Homo erectus fossils were discovered in China during the 1920s and 1930s. These discoveries confirmed this was indeed a widespread human species that had inhabited enormous regions across Africa, Asia, and Europe. Their jaw structures were remarkably more robust than both contemporary humans and living apes, which would have enabled their jaws to withstand tremendous rotational forces during biting or chewing, potentially allowing for extraordinarily powerful stresses while consuming food. Fascinatingly, their dental remains reveal a significantly higher frequency of microscopic pits in their premolars and molars when compared to earlier species like Homo habilis. This pattern indicates a dietary preference for brittle, hard foods, possibly enhanced by their sophisticated tool usage, which enabled them to process a much broader spectrum of foods than their evolutionary predecessors. Similar to contemporary humans, Homo erectus demonstrated remarkable size variation, spanning from 4'9" to 6'1" in height and weighing between 40 to 68 kilograms. This extensive variation likely resulted from regional climate differences, mortality patterns, and nutritional availability among populations. This degree of phenotypic plasticity, the capacity to display significant physical responses to environmental pressures, is exceptionally rare and only documented in modern humans and Homo erectus. Homo erectus displayed sexual dimorphism, meaning noticeable differences in body size and sometimes other physical traits between males and females. Generally, male Homo erectus individuals appeared larger and more physically robust than females. Scientists infer this sexual dimorphism from fossil evidence, including variations in skeletal dimensions and structural characteristics. Remarkably, 971 500-year-old footprints created by at least 20 different individuals near Illoret, Kenya, demonstrate that Homo erectus exhibited more pronounced sexual dimorphism than modern Homo sapiens, though less extreme than highly dimorphic apes such as gorillas and extinct species like Australopithecus afarensis and Paranthropus robustus. These footprints provide an extraordinary glimpse into a critical transitional phase in hominin social behavior, suggesting organizational structures positioned somewhere between the extremely male-dominated hierarchies of great apes and the more balanced social arrangements of modern humans. These identical footprints also unveil something truly remarkable about Homo erectus locomotion. They demonstrate that Homo erectus became the first species in our human lineage to possess a genuinely modern human gait. The footprint evidence and skeletal remains suggest they possessed approximately identical limb configurations and proportions as contemporary humans, implying human-like movement patterns that would have been dramatically more efficient for covering long distances than the walking patterns of earlier human species. Homo erectus also became the first in our evolutionary lineage to develop human-like shoulder anatomy. indicating capabilities for high-velocity throwing. This adaptation would have provided a tremendous evolutionary advantage, allowing them to accurately launch rocks, wooden spears, or other projectiles, significantly improving their ability to hunt large game for valuable, calorie-dense meat. This represents a stark contrast to their early hominin predecessors such as Homo habilis, who retained chimpanzee-like shoulder structures completely unsuited for precise object throwing. When examining the fossil record, it becomes abundantly clear that Homo erectus represented a revolutionary transformation in human evolution, marking the emergence of a species that, while still distinctly different from us in numerous ways, possessed a comprehensive collection of physical and cognitive adaptations that would characterize the human lineage for millions of years ahead. These weren't merely incrementally improved versions of earlier hominins, they represented a groundbreaking new category of human equipped with bodies engineered for endurance, accuracy, and remarkable adaptability. However, their physical adaptations were merely the foundation of what made Homo erectus so extraordinarily successful. As primates and mammals, we humans display the distinctive characteristic that distinguishes us from most of our evolutionary relatives: relatively hairless skin. While aquatic mammals like whales and dolphins, along with elephants, share this trait, most primates and mammals typically possess thick, furry coats. So when did humans shed their body hair? And what drove this transformation? It appears Homo erectus became the first member of the genus Homo to develop this hairless condition, with studies indicating this adaptation appeared at least 1.2 million years ago. But to comprehend why humans possess significantly less body hair than the other primates, we must understand that mammalian body hair isn't simply decorative. It shields skin from injuries, parasites, heat, cold, and ultraviolet radiation. So why would an early human species evolve to abandon this protective barrier? The most widely accepted evolutionary explanation centers on heat regulation. When early genus Homo members transitioned from shaded forest environments to open savanna living, losing body hair and developing enhanced sweat glands made cooling their bodies much easier during prolonged physical activity. This environmental transition also sparked a major dietary shift from predominantly vegetarian to increasingly hunting-focused lifestyles. Chasing prey across scorching savannas dramatically intensified the need for effective body temperature control. Here's where everything becomes truly captivating. Anthropologist and paleobiologist Nina Jablonski proposes that the capacity to release excess body heat through efficient sweating actually enabled the dramatic brain enlargement process, since the brain represents our most temperature-sensitive organ. Therefore, fur loss wasn't merely about maintaining cool temperatures. It potentially enabled additional adaptations, both physical and behavioral, that separated humans from other primates. Some researchers suggest sexual selection accelerated these evolutionary changes. By preferentially choosing more hairless partners, Homo erectus may have expedited modifications initially triggered by natural selection pressures. This hairless adaptation introduces another intriguing question. What about skin pigmentation? Most mammals possess light skin beneath protective fur, and biologists believe early human ancestors began similarly. But this pattern changed with Homo erectus. Genetic analysis indicates that elevated activity in the melanocortin-1 receptor gene, responsible for producing dark skin, traces back to Homo erectus approximately 1.2 to 2 million years ago. Dark pigmentation, specifically melanin, functioned as natural sunscreen, helping prevent skin damage and reducing risks of conditions like skin cancer in high sun exposure regions. Possessing dark skin would have provided survival advantages for Homo erectus by offering superior protections against intense solar radiation. However, as Homo erectus populations expanded toward higher latitudes with reduced sunlight intensity, they potentially developed lighter skin pigmentation to prevent vitamin D deficiency. Consider contemporary human migration patterns. The earliest sapiens originated in Africa under tropical sun conditions, then migrated into Asia and eventually spread throughout Europe. Given that Homo erectus had considerably more time to disperse across and adapt to Asian and European environments, it's logical to assume they would have demonstrated similar skin tone flexibility to what we observe in modern human populations today. Supporting this hypothesis, a 500,000 to 300,000-year-old Homo erectus specimen from Turkey was diagnosed with the earliest documented case of tuberculous meningitis, a condition typically worsened in dark-skinned individuals living at higher latitudes due to vitamin D deficiency. This suggests this individual may have possessed darker skin in an environment where lighter pigmentation would have been more advantageous, perhaps indicating that skin colour adaptation was still developing in these northern Homo erectus populations. Another captivating aspect of Homo erectus biology concerns brain development patterns. A 1.8 million-year-old Homo erectus specimen named Mojokerto-1, discovered in Java, who died at approximately 1 year of age, already possessed 72 to 84% of average adult brain size. Compare this to modern human 1-year-olds who typically achieve only around 50% of their adult brain capacity. This reveals something extraordinary. Homo erectus maintained a faster brain growth trajectory more similar to great apes than to modern humans. This indicates that Homo erectus probably wasn't cognitively comparable to contemporary humans, and that our extended childhood and prolonged dependency period due to the extensive time required for brain maturation evolved much later in human evolution, perhaps in the modern human and Neanderthal common ancestor. While Homo erectus might not have achieved the intellectual capabilities of modern humans, they would have remained at the pinnacle of the cognitive hierarchy on our planet during their era. Their enlarged brains and sophisticated tools indicate problem-solving abilities and social complexity far exceeding earlier human species. Some scientists differentiate between African erectus, which they call Homo ergaster, and Asian erectus, which they term Homo erectus sensu stricto, because of slightly different characteristics. For instance, African individuals' faces tend to be taller and less broad across the eye socket regions. However, it's important to note that modern humans today also display regional variations in physical characteristics, yet we don't get categorized into separate species classifications. Many scientists now simply group them together as Homo erectus, which not only makes greater taxonomic sense, but also streamlines discussions about their evolutionary history. Speaking of evolution, where did Homo erectus originate? It's generally accepted that Homo erectus descended from an earlier species, Homo habilis, an early genus Homo member, who still retained ape-like characteristics, including elongated arms and a moderately projecting face. This evolutionary transition occurred roughly 2 million years ago. However, this straightforward evolutionary pathway has been questioned because Homo habilis and Homo erectus fossils indicate they coexisted for at least 500,000 years. This temporal overlap indicates either that a specific isolated population of Homo habilis transformed into Homo erectus, while other Homo habilis groups remained unchanged, or that Homo erectus might have descended from an early, still undiscovered primitive Homo species. The birthplace of Homo erectus remains heavily contested, as fossils dating approximately 2 million years ago have been discovered in both Africa and China. A 2011 research study proposed that Homo habilis first migrated to West Asia from Africa, where early Homo erectus subsequently developed before spreading to East Asia, Southeast Asia, and eventually returning to Africa, where they ultimately evolved into modern humans. Alternative studies have suggested that Homo erectus originated in Africa, where separate populations eventually gave rise to later hominin species such as Homo heidelbergensis, and ultimately our own species, Homo sapiens. At the beginning of their temporal range around 1.9 million years ago, Homo erectus shared East African territories with several other early human species including Homo rudolfensis, Homo habilis, and Paranthropus boisei. Sometimes fossils from these different species have been discovered at identical locations, suggesting they shared territorial boundaries and competed for similar resources. At their temporal range's conclusion around 100,000 years ago, Homo erectus possibly coexisted with Homo floresiensis in Indonesia. Given the time frame and geographical positioning, there's also substantial likelihood they may have encountered and even interbred with the enigmatic Denisovans in Southeast Asia. This could potentially explain the mysterious ghost genomes detected in Denisovan remains, which scientists have managed to extract from merely a pinky bone fragment and 2 molars discovered in Denisova Cave in Siberia. How did Homo erectus approach hunting and food gathering? Persistence hunting has been proposed as their primary strategy for meat acquisition, thanks to their bipedal locomotion, lean body structure, and hairless skin that enabled efficient temperature regulation through sweating during extended pursuits. Homo erectus could potentially maintain running speeds for up to 5.5 hours without water consumption. This would have provided them tremendous advantages in outlasting prey, establishing them as exceptionally successful hunters. Their hunting tactics and prey preferences would have varied based on available resources in their respective regions and habitats. However, Homo erectus is believed to have been remarkably versatile hunter-gatherers, targeting diverse animals for sustenance. Archaeological evidence indicates they hunted birds, deer, wild boar, and even massive elephants. In 1988, scientists discovered elephant remains and numerous dismembered skeletons of giant, now extinct baboons, alongside 400 flake tools near Lorgusalie, Kenya, dating between 790,000 and 992,000 years ago. Many bones displayed obvious cut marks, and the animal's limbs were conspicuously absent. If these animals were indeed hunted rather than scavenged, it would have required extraordinary skill to defeat such formidable creatures, suggesting Homo erectus hunted in coordinated groups, which implies they likely possessed some form of primitive language or communication system. It can reasonably be assumed that similar to present-day hunter-gatherers such as African sand bushmen and Australian aboriginals, meat from hunting comprised only part of Homo erectus's diet. Other food sources likely included snakes, birds and their eggs, locusts, scorpions, centipedes, tortoises, rodents, hedgehogs, fish, and crustaceans. Even children could have captured many of these creatures, as they still do in Africa's Kalahari Desert today, before being permitted to accompany older males on more dangerous hunts. Plant foods such as fleshy leaves, fruits, nuts, roots, and tubers must have also been crucial dietary components. Accumulations of hackberry seeds, for example, were discovered in Zhoukoudian cave deposits in China, where the famous Peking man Homo erectus fossils were unearthed. There appears little doubt that Homo erectus maintained omnivorous eating habits, an opportunistic dietary strategy offering maximum flexibility. Modern humans represent the most opportunistic of all living primates, and Homo erectus was likely among the earliest human species to develop this characteristic, providing the species with remarkable adaptability and evolutionary flexibility. Though Homo erectus were skilled hunters for their era, they would have undoubtedly served as prey for fierce predators sharing their environments. 2/3 of Homo erectus fossils discovered in Longshan, China, contain damage consistent with carnivore teeth marks, most likely from hyenas. One well-preserved crushed Homo erectus skull found at Longshan displays puncture marks perfectly matching the teeth of the extinct giant hyena Pachycrocuta brevorostris, or short-faced hyena. Another cave at Zhoukoudian, China contained skeletal elements of Homo erectus individuals scattered across cave floor areas up to 9 meters in diameter. Analysis revealed that 67% of these Homo erectus remains showed bite marks or other modifications attributed to large mammalian carnivores. Homo erectus likely experienced intense competition and constant vigilance due to dangerous predator presence, requiring heightened states of caution and fear. Their ability to form protective groups and collaborate would have been absolutely crucial for survival. However, for some unfortunate individuals, they definitely became meals for ancient predators. What tools did Homo erectus utilize? They began with simple yet effective hand axes for hunting and butchering animals. But later in their evolutionary timeline, these hand axes became increasingly sophisticated, marking significant improvements in their tool technology and demonstrating the mental advances these early humans achieved. The earliest hand axes associated with Homo erectus are tools of the type discovered in Olduvai Gorge, Tanzania, where they were found in large quantities. These older implements were characterized by simple construction, predominantly utilizing core forms. These cores were river pebbles or similar rocks that had been struck by spherical hammerstones to cause conchoidal fractures, removing flakes from one surface to create an edge and often a sharp tip. The blunt end of these tools is called the proximal surface, while the sharp end is the distal surface. Using percussion technology while grasping the proximal surface, the hominin would bring the distal surface down forcefully on objects they wished to detach or shatter, such as bones or tubers. Skip ahead several 100,000 years in Homo erectus tool-making evolution, and you encounter more complex hand axes called Acheulean, named after the Saint-Achille site in France. These tools developed around 176 million years ago. Acheulean tools were characterized not by a core, but by a biface. A stone tool worked on both sides. The most notable form was the hand axe. The earliest Acheulean axes appeared in the West Turkana area of Kenya and around the same time in southern Africa. Acheulean axes are larger, heavier, and possess sharp cutting edges that are chipped from opposite sides into a teardrop shape. In contrast to an Oldowan tool, which results from a fortuitous and probably spontaneous operation to obtain one sharp edge on a stone, an Acheulean tool represents the planned result of a sophisticated manufacturing process. The manufacturer begins with a blank, either a larger stone or a slab knocked off a larger rock. From this blank, the maker removes large flakes to be used as cores. Standing a core on edge on an anvil stone, the maker strikes the exposed edge with centripetal blows of a hard hammer to roughly shape the implement. Then the piece must be worked over again, or retouched with a soft hammer of wood or bone, to produce a tool finely chipped all over, consisting of two convex surfaces intersecting in a sharp edge. These more complex Acheulean hand axes endured for more than 1 million years with minimal changes from the earliest versions, indicating their efficiency and suggesting no need for improvement. Though fossil remains of the toolmakers themselves aren't always preserved alongside the tools, these hand axes clearly document the evolution of innovation, craftsmanship, acquired intelligence, and social behaviour in a pre-modern human community over a million-year interval. Homo erectus produced other tools as well. Evidence shows they crafted implements from shells at sites in Sangaran and Trinil. Spherical stones measuring 6 to 12 centimetres and 2.4 to 4.7 inches in diameter are frequently found in African and Chinese Lower Paleolithic sites, and these were potentially used as boles, throwing weapons consisting of weights connected by cords used to entangle prey. Beyond tools, did Homo erectus construct shelters? Evidence suggests they did build structures for protection. There are indications that Homo erectus constructed branch huts up to 50 feet long for shelter, sometimes with stone slabs or animal skins for floors. The first houses were thought to be simple windbreaks made of animal skins stretched over frames. The oldest recognised shelter from this era was discovered at the Terra Amata site near Nice, France in 1960. The shelter was a collection of 12 individual oval structures that ranged from 26 feet to 49 feet in length with widths between 13 and 20 feet. Homo erectus used fire to keep warm, and the huts within these shelters were ringed with small rocks to form fire lines around the edges of dug pits for wood. Another remarkable site was discovered near present-day Bilsingsleben in eastern Germany, where ancient humans, thought to be Homo erectus, though some argue they may have been Homo heidelbergensis, lived around 350,000 years ago. They constructed shelters similar to those of Bushmen in southern Africa, circular structures with bone and stone foundations between 9 and 13 feet across. In the middle of each circle, archaeologists found an elephant tusk, which they speculated might have served as a centre post. These discoveries point to a species with far more complex behaviour than previously imagined, one capable of modifying their environment to create protected living spaces, using fire for warmth and protection, and organising their living areas in ways that suggest social structure and cooperation. One of the most revolutionary aspects of Homo erectus culture was their mastery of fire. The controlled use of fire fundamentally transformed human evolution, allowing our ancestors to keep predators at bay, extend their waking hours beyond sunset, cook their food, and eventually colonize colder regions of the planet. Being able to produce and maintain fire meant that Homo erectus gained unprecedented control over their environment and diet in ways no previous species had achieved. Cooking food proved particularly revolutionary. Cooked meat not only becomes significantly safer with reduced pathogens, but it's also dramatically easier to digest. The cooking process breaks down resistant fibres in both meat and plant materials, enabling more efficient nutrient extraction with substantially less digestive effort. This may have contributed to the gut size reduction observed in Homo erectus fossil records, compared to earlier hominins, potentially liberating energy for brain development. However, determining exactly when our ancestors first controlled fire remains one of paleoanthropology's most fiercely debated topics. Why? Because campfires extremely rarely preserve well over extended periods, much less for hundreds of thousands or millions of years. Despite these preservation obstacles, Homo erectus is widely recognized as the first human ancestor to have utilized fire, though the precise timing remains highly disputed. The earliest claimed fire sites include Kubifora in Kenya, dating to approximately 1.5 million years ago, and Wonderwork Cave in South Africa, with evidence suggesting controlled fire use as early as 1.7 million years ago. However, these early dates remain controversial among researchers, with some arguing the evidence isn't definitive. The first Homo erectus firekeepers are thought to have simply transported and maintained naturally occurring fires for extended periods rather than generating fire themselves. They might have opportunistically collected fesa from lightning strikes or natural brush fires, then carefully sustained it for as long as possible. This would require knowledge of slow-burning materials like dried dung that could maintain flames for extended durations. Fascinatingly, fire becomes markedly more abundant in the broader archaeological record after 400,000 to 300,000 years ago. This significant increase could indicate either advancements in fire-making techniques or perhaps suggest that our human ancestors only opportunistically used fire until this period when they finally mastered reliable fire-starting methods. It's entirely possible that fire-starting technology was invented, lost, reinvented, and independently discovered multiple times by different Homo erectus communities rather than being invented in one location and spreading throughout their range. The challenges of preserving fire-making tools in the archaeological record make this extremely difficult to determine with certainty. The earliest conclusive evidence of deliberately constructed hearths comes from Gesher Benot Yaakov in Israel, dating to over 700,000 years ago. What makes this site particularly compelling is that fire is recorded in multiple archaeological layers in an area near water, both characteristics that would be uncharacteristic of natural wildfires, strongly suggesting intentional controlled use. The advent of controlled fire use had profound social implications as well. The long-standing tradition of people gathering around campfires telling stories likely originated with Homo erectus, and this practice would have had massive effects on the evolution of social capabilities and possibly the complexity of human communication systems. Gathered around the safety and warmth of a fire in the evening, early humans would have had new opportunities for social bonding, knowledge sharing, and collective planning. Some researchers have proposed that increased social activity around campfires facilitated the need for more complex ideas to be communicated, potentially driving the development of more sophisticated language capabilities. The firelight would have extended waking hours into the night, creating time for social activities beyond mere survival tasks, perhaps the beginnings of culture as we understand it. Beyond these technological and social advances, archaeological evidence reveals darker aspects of Homo erectus society that force us to reconsider our views of these ancient humans. Multiple Homo erectus skulls found in India show numerous head wounds. Were these caused by warfare between groups, hunting accidents, or competition within groups? It's difficult to say with certainty, but they suggest violence was present in Homo erectus society. Even more provocatively, some archaeological sites contain human bones with cut marks similar to those made with Homo erectus tools on butchered animals. These have been discovered in sites ranging from South Africa to Croatia, leading some scientists to speculate that cannibalism may have been part of Homo erectus behavior for hundreds of thousands of years. This wouldn't be entirely surprising from an evolutionary perspective. Evidence suggests that even Homo sapiens engaged in cannibalistic practices in the not-so-distant past. In Gough's Cave in the United Kingdom, anthropologists discovered bite marks on 15,000-year-old human bones that appear to show deliberate consumption. The marks suggest the ancient consumers were attempting to scrape off every millimetre of nutritious muscle. Researchers also found hundreds of filleting marks and ritualistic incisions on bones and even unearthed skulls apparently modified for use as cups. Similarly, Homo erectus skulls dated to 500,000 years old found in caves at Longshan in China appear to have been severed from the body and preserved presumably as trophies. Some researchers speculate the purpose may have been ritualistic, perhaps to symbolically obtain the strength or qualities of the deceased. However, critics of these claims suggest the marks on the skulls might have been made by giant hyenas rather than other hominins. Could Homo erectus communicate through language? This question touches on one of the most crucial transitions in human evolution, the development of language. Some scientists have theorized that Homo erectus must have possessed some form of rudimentary language because they needed to communicate to organize hunts and pass on information about tool-making. However, the parts of the Homo erectus brain associated with reasoning, symbolism, and imagination appear to have been relatively underdeveloped compared to modern humans. The frontal lobe, where complex thinking takes place in modern humans, was comparatively small in Homo erectus. Additionally, the spinal cord canal in Homo erectus vertebrae was narrower than in modern humans, suggesting limited nerve pathways between the brain and the muscles controlling breathing and vocalization. Many researchers believe Homo erectus didn't possess the FOXP2 gene, often called the language gene, in its modern form. This gene, which plays a crucial role in neural development necessary for language and speech, is found in its current form only in modern humans and Neanderthals. Based on these anatomical constraints, many scientists think Homo erectus likely communicated with simple vocalizations, gestures, and facial expressions rather than complex language with grammar and syntax. They may have used a limited vocabulary of distinct sounds to convey basic information about food sources, dangers, or social status. Yet even in this basic form, communication among Homo erectus would have represented a significant advance beyond previous hominin species. The knowledge required to craft Acheulean and stone tools, for instance, would have been difficult to transmit without some form of demonstrative communication combined with vocal instruction. If we think of language capabilities on a spectrum with modern human language being the most complex, Homo erectus might represent a crucial intermediate stage, not yet capable of the abstract and symbolic communication we take for granted, but far more sophisticated than anything that had come before. In essence, if modern humans represent the pinnacle of language evolution, comparable to today's advanced technology, then Homo erectus might be likened to the Model T Ford of language, rudimentary by our standards, but revolutionary for its time and laying crucial foundations for what would follow. Did Homo erectus create art? Until recently, the earliest evidence of geometric art was dated from 70,000 to 100,000 years ago. Scratched patterns found in South African caves created by early Homo sapiens. These engravings have been interpreted as signs of behavioral modernity, our species' unique cognitive journey into a sophisticated world of abstraction and symbolism. But a remarkable discovery has pushed the origins of art back much further, potentially to Homo erectus. A zigzag pattern found on a fossilized shell from Java, Indonesia, has been dated to approximately 430,000 years ago, making it potentially the world's earliest known engraving, and demonstrating that Homo erectus possessed both the manual dexterity and possibly the symbolic thinking necessary for artistic expression. The pattern consists of a zigzag line with 3 sharp turns producing an M shape, a set of more superficial parallel lines, and another zigzag with 2 turns producing a W shape. A study conducted by marine biologist Josephine Jordans and her colleagues concluded that the morphology of the zigzags, internal morphology of the grooves, and differential roughness of the surrounding shell area demonstrates that the grooves were deliberately engraved and predate shell burial and weathering. Other potential evidence of Homo erectus artistic expression includes the Middle Pleistocene Venus of Tan Tan and Venus of Berechat Ram, objects postulated to have been modified by Homo erectus to resemble human forms. These items were mostly formed by natural weathering, but appear to have been slightly modified to emphasize certain grooves suggesting hairlines, limbs, and eyes. The former has traces of pigments on the front side, possibly indicating it was intentionally coloured. Homo erectus was also the earliest human species known to have intentionally collected red-coloured pigments, namely ochre. This behaviour is recorded as early as the Middle Pleistocene, with ochre lumps at Olduvai Gorge, Tanzania, associated with the 1.4 million-year-old Olduvai hominid 9, and at Ambrona, Spain, which dates to 424,000 to 34,000 years ago. In both locations, the ochre appears to have been struck by a hammerstone and purposefully shaped and trimmed. At Terra Amata in France, which dates to 425,000 to 325,000 years ago, red, yellow and brown ochres were recovered in association with pole structures. The ochre was probably heated to achieve such a wide colour range. Since it's unclear if Homo erectus could have used ochre for any practical application, these findings might indicate that Homo erectus was the earliest human species to have exhibited a sense of aesthetics and to think beyond simple survival needs. One of the most surprising capabilities attributed to Homo erectus is seafaring. Peculiar artefacts discovered on isolated islands that were never connected to mainland areas during the Pleistocene may show seafaring by Homo erectus as early as 1 million years ago. In Indonesia, they had arrived on the islands of Flores, Timor, and Roti, which would have necessitated crossing the Lombok Strait, also known as Wallace's Line, at least before 800,000 years ago. This crossing wouldn't have been easy. The Lombok Strait is 24 miles wide, 250 meters deep, and has fierce currents due to its location as a main channel for the Indonesian throughflow, the maritime connection between two of the world's great oceans, the Indian and the Pacific. These oceans have differences in temperature and sea levels, creating treacherous water conditions. If Homo erectus truly did cross this strait, it suggests they had the capability to build sophisticated watercraft and navigate dangerous waters, a level of technological achievement far beyond what was previously attributed to them. This would also strongly indicate advanced communication abilities. If these ancient humans possessed the ability to coordinate paddling expeditions to distant islands, they absolutely must have developed sophisticated spoken communication systems to strategize and accomplish such monumentally challenging ocean crossings. Archaeological discoveries also indicate that Homo erectus communities may have established comprehensive healthcare practices and mutual support networks. The most ancient documented example of collective medical care for disabled or injured community members involves a 1.77 million-year-old Homo erectus individual discovered in Georgia, who had permanently lost every tooth except one due to advanced aging or severe periodontal disease. This represents the earliest recorded case of complete chewing disability found in any fossil evidence. Remarkably, this person continued living for multiple years following this debilitating condition. Being completely unable to process tough food materials, they undoubtedly depended on softened plant matter or pre-processed animal proteins, quite possibly receiving direct assistance from fellow group members who took responsibility for their survival. Another extraordinary case involves a 1.5 million-year-old adolescent specimen nicknamed the Turkana Boy, who received a medical diagnosis of juvenile spinal disc herniation. Since this individual was still experiencing physical development, this spinal condition triggered moderate scoliosis development. Such medical conditions characteristically generate chronic lower back agony and sciatica nerve pain radiating throughout the entire leg, severely limiting fundamental activities including walking, bending, and countless other essential daily movements. The remarkable fact that this young person managed to survive well into their teenage years despite these profound physical limitations strongly suggests the existence of organized community medical care and dedicated group support systems. A specimen dating between 1 million and 700,000 years ago from Java presents clearly visible osteophyte bone growth formations on the femur, most likely caused by Paget's disease affecting bone structure and osteopetrosis, creating abnormal bone density increases. These debilitating medical conditions probably developed from skeletal fluorosis, triggered by consuming food materials contaminated with fluorine-saturated volcanic ash deposits, since this specimen was excavated from geological layers heavily filled with volcanic ash residue. This particular individual would have experienced tremendous difficulty with basic locomotion and food-gathering activities, essentially representing a survival burden to their community when viewed through purely practical survival calculations. Yet they managed to live for many years while coping with these severe injuries, once again providing compelling evidence of sophisticated group medical care practices. To understand the significance, consider that modern livestock grazing in volcanic ash-contaminated fields typically succumb to acute fluorine poisoning within mere days or weeks. The extended survival of this Homo erectus individual despite similar toxic exposure levels clearly suggests intentional medical intervention and sustained care from other community members. These documented cases of apparent healthcare systems within Homo erectus societies reveal something absolutely profound about their social organizational structures. Rather than simply abandoning sick or injured members who could no longer make full contributions to group survival, as might be anticipated in societies focused exclusively on immediate survival necessities, Homo erectus communities appear to have actively supported their most vulnerable members, enabling them to survive despite facing serious health complications. This behavioral pattern suggests remarkable levels of compassion, emotional bonding, and perhaps even primitive understanding of medical caregiving that extends far beyond the stereotypical primitive caveman imagery typically associated with the early humans. It demonstrates that some of our most fundamental human values, particularly caring for sick and vulnerable community members, may have evolutionary origins extending back nearly 2 million years, long before our own species ever emerged on this planet. So what ultimately sealed the fate of Homo erectus? After flourishing for nearly 2 million years, representing an almost incomprehensibly vast time span compared to our own species' relatively brief existence, Homo erectus eventually vanished completely from the fossil record. However, the question of what caused their extinction remains the subject of intensive ongoing research and scholarly debate. Their disappearance was most likely triggered by multiple interconnected factors, but the primary scientific theory focuses on a devastating combination of dramatic climate change and intensifying competition from later, more technologically advanced human species, including Homo heidelbergensis, Neanderthals, Denisovans, and eventually modern humans. A dedicated research team discovered that Homo erectus experienced catastrophic loss of a significant portion of their habitable climate zones just before they disappeared entirely from fossil evidence. This critical scientific insight helps explain their eventual extinction after maintaining such a remarkably extended evolutionary reign. Species populations generally flourish when they possess access to large interconnected territorial areas available for their use. However, when livable regions undergo shrinkage and fragmentation into small geographically isolated patches, species enter what ecological scientists call an extinction vortex, representing a devastating downward spiral toward complete species disappearance. These dramatic reductions in habitable territory resulted directly from sudden catastrophic climatic transformations. The research team determined that Homo erectus became extinct during the last major glacial period, which commenced approximately 115,000 years ago, representing quite possibly the coldest climate conditions the species had ever encountered throughout their entire lengthy evolutionary history. Unlike subsequent human species such as Neanderthals, who successfully developed specialized biological and cultural adaptations for surviving extreme cold conditions, Homo erectus appears to have completely lacked the cognitive flexibility and technological innovation capabilities necessary to survive such dramatic environmental shifts. Their tool-making technology remained essentially unchanged for hundreds of thousands of years, suggesting a certain behavioral conservatism in their approach to confronting environmental challenges. The final stronghold of Homo erectus existed on Java Island in Indonesia, where they managed to persist long after disappearing from everywhere else. This extended survival in Java can be explained by the island's distinctive geography and climate patterns. Being positioned much closer to the equator, Java experienced significantly less dramatic temperature fluctuations during glacial periods. Additionally, its geographic isolation provided protection for these final Homo erectus populations from competition with more advanced human species that were rapidly expanding across mainland Asian territories. However, even this last sanctuary eventually became completely uninhabitable for them. As climate patterns shifted dramatically, Java's environment transformed from the open woodland habitat traditionally associated with Homo erectus survival to rapidly expanding dense rainforest coverage. These thick forest environments would have presented entirely different challenges for hunting strategies, food gathering techniques, and basic movement patterns, challenges that Homo erectus, with their relatively static technology and rigid behavioral patterns, may have been completely unable to overcome. One controversial scientific study even suggested that behavioral laziness and conservative tendencies directly contributed to their ultimate demise. Researchers pointed to archaeological sites in the Sunda region of Indonesia, where Homo erectus consistently used locally available low-quality stone materials for tool creation rather than travelling slightly greater distances to obtain superior materials that would have produced dramatically more effective implements. This apparent reluctance to innovate or invest additional effort for achieving improved outcomes might have become severely maladaptive as the environmental conditions changed rapidly. However, this interpretation has faced significant criticism from many paleoanthropologists as imposing modern value judgments on ancient hominins who operated within completely different environmental constraints and survival pressures. It's absolutely crucial to recognise that the concept of extinction might not represent the most accurate way to describe what actually happened to Homo erectus populations. Many researchers currently believe that Homo erectus didn't simply die off completely, but instead evolved into entirely new species of hominins, like Homo heidelbergensis in various regions. This evolutionary process likely involved extensive interbreeding with other hominin species as they came into territorial contact, creating incredibly complex patterns of genetic exchange that are only now beginning to be understood through revolutionary ancient DNA analysis techniques. The remarkable saga of Homo erectus opens up mind-bending questions about human evolutionary pathways and the fundamental nature of species classifications. Instead of perceiving human evolution as a straightforward linear progression advancing from one species to another, mounting evidence increasingly reveals an intricate branching network of diverse hominins who frequently coexisted, battled for resources, and occasionally interbred with one another. Homo erectus doesn't represent some failed evolutionary experiment or a developmental dead end, but rather serves as an absolutely essential foundation upon which all subsequent human diversity would eventually construct itself. One absolutely captivating dimension of Homo erectus that deserves deeper exploration involves their extraordinary adaptability to extreme high elevation environments. Revolutionary discoveries now suggest that Homo erectus successfully colonized mountainous high-altitude territories much earlier than scientists previously imagined possible. Archaeological evidence recovered from the Tibetan Plateau clearly indicates that hominins were establishing permanent settlements at elevations exceeding 4,000 meters as early as 1.6 million years ago, precisely during the period when Homo erectus dominated as the primary hominin species throughout East Asian territories. Surviving at such punishing high altitudes creates devastating physiological obstacles. Contemporary humans who lack proper adaptation to elevated environments routinely experience hypoxia or severe oxygen deficiency, which triggers altitude sickness, dramatically reduced physical performance, and potentially life-threatening medical conditions including pulmonary or cerebral edema. The stunning fact that Homo erectus apparently managed to flourish in these harsh environments strongly suggests they successfully developed specialized biological adaptations enabling them to cope with severely reduced oxygen availability, adaptations that may have subsequently been transmitted to modern high-altitude populations through interbreeding events or shared evolutionary ancestry. This remarkable high-altitude colonization achievement demonstrates yet another extraordinary way that Homo erectus proved incredibly adaptable, aggressively expanding into environmental conditions that would have appeared absolutely forbidding to earlier hominin species. From coastal seaside environments to towering mountain ranges, from dense tropical forests to expansive open savannas, Homo erectus managed to establish thriving communities across an absolutely astonishing variety of ecological habitats, displaying a remarkable versatility that clearly foreshadowed the eventual global expansion of later human species. Another fascinating area of intensive ongoing research involves Homo erectus relationships with aquatic environments beyond the compelling evidence for possible seafaring capabilities mentioned previously. Some researchers have enthusiastically proposed what's scientifically known as the aquatic ape hypothesis to explain certain distinctive Homo erectus physical characteristics. This highly controversial theory suggests that numerous human traits, including our distinctive relative hairlessness, unique subcutaneous fat distribution patterns, and sophisticated voluntary breath control abilities, might have evolved during an extended evolutionary phase when our ancestors spent considerable time in shallow water environments, possibly wading, swimming, and actively foraging for marine food resources. While mainstream paleoanthropological communities have predominantly rejected the most extreme versions of this hypothesis, mounting evidence increasingly demonstrates that coastal and riverine food resources played tremendously important roles in Homo erectus subsistence strategies. Archaeological excavation sites located along ancient shorelines clearly show compelling evidence of systematic shellfish consumption, sophisticated fish processing techniques, and extensive aquatic resource utilization dating back hundreds of thousands of years. The remarkable ability to successfully exploit these incredibly rich food sources, particularly those high in proteins and omega-3 fatty acids that actively support brain development processes, may have provided absolutely crucial nutritional advantage. Some researchers enthusiastically speculate that consistent access to these brain-boosting nutrients might have significantly contributed to the encephalization process, or increasing brain size that fundamentally characterizes Homo erectus evolutionary development. We've examined extensively Homo erectus biological characteristics and technological achievements, but what about their potential emotional experiences and complex social relationships? While we can never definitively know the inner psychological experiences of extinct species, the archaeological evidence provides some absolutely tantalizing clues about their emotional lives. The documented care for injured and disabled community members mentioned earlier strongly suggests social bonds that transcended mere survival utility calculations. The remarkable fact that Homo erectus groups actively supported members who could no longer fully contribute to essential subsistence activities clearly indicates deep emotional attachments and perhaps even sophisticated concepts of reciprocal care that extended far beyond immediate family units. Some archaeological sites also suggest possible ritual behaviours and ceremonial activities. The deliberate arrangement of stone tools and animal remains at certain Homo erectus sites displays patterns that appear intentionally structured rather than purely functional or accidental. While we must remain cautious about projecting modern human symbolic thinking capabilities onto ancient species, these intriguing patterns hint at the developmental beginnings of ritualized behaviors that might have reinforced group identity formation and social cohesion maintenance. The possible systematic collection and intentional modification of objects without obvious utilitarian purposes, like the ochre pigments and potentially symbolic items mentioned earlier, further suggests that Homo erectus may have possessed the fundamental cognitive foundations necessary for aesthetic appreciation and perhaps even rudimentary symbolic thought processes. These remarkable capacities, while likely much less developed than in modern humans, would represent absolutely crucial evolutionary steps toward the incredibly rich symbolic and cultural worlds that characterize later human species. An absolutely intriguing area of scientific speculation concerns how Homo erectus might have understood and interpreted their surrounding world. Without access to complex language systems or writing technologies, their conceptual frameworks would have been primarily rooted in direct experiential knowledge, rather than abstract categorization systems. Their accumulated knowledge would have been deeply embedded within specific landscapes and environmental contexts, transmitted through hands-on demonstration and careful imitation rather than explicit verbal instruction. Some cognitive archaeologists enthusiastically suggest that Homo erectus may have possessed what scientists call mimetic culture, representing the sophisticated ability to represent knowledge through intentional bodily movements including gesture, dance, and non-linguistic vocalization systems. This remarkable form of communication, significantly more sophisticated than that demonstrated by great apes but considerably less complex than fully syntactic language, would have enabled them to effectively share crucial information about tool-making techniques, hunting strategies, and environmental knowledge. This mimetic capacity might explain how Homo erectus successfully managed to maintain relatively consistent tool-making traditions across vast geographic areas and extended time periods without written instructions or complex verbal explanations. The remarkable stability of their technological traditions spanning hundreds of thousands of years suggests highly effective systems for knowledge transmission that relied primarily on careful observation and precise imitation. The social organizational structures of Homo erectus groups remain largely speculative, but some valuable clues emerge from comparative studies with both great apes and modern hunter-gatherer societies, as well as from the archaeological record itself. The sexual dimorphism observed in Homo erectus, while less pronounced than in great apes, suggests males were somewhat larger than females, which might indicate social structures featuring some degree of male dominance or competitive hierarchies. However, the cooperative hunting strategies clearly evidenced at sites like Olorgesailie in Kenya demonstrate coordination between multiple individuals, representing a level of sophisticated collaboration that typically requires relatively egalitarian social relationships. The most probable scenario suggests that Homo erectus lived in small, flexible bands with fluid membership patterns, similar to but perhaps less organisationally complex than those of modern hunter-gatherer societies. Within these groups, accumulated knowledge about natural resources, territorial boundaries, and essential techniques would have been shared through direct demonstration and accumulated through extensive experience. Community elders might have held particular value as living repositories of environmental knowledge, knowing precisely where to locate water sources during severe droughts, which plant species were edible during different seasons, or how to predict animal migration patterns based on subtle environmental indicators. As we carefully piece together the comprehensive Homo erectus story from fragmentary fossil and archaeological evidence, one fundamental truth becomes increasingly clear. These were definitely not simple primitive creatures barely removed from their ape ancestors. They were remarkably complex beings with extraordinary adaptations, rich social lives, and sophisticated cognitive capacities that enabled them to flourish across vast spans of time and geographical space. Their profound legacy continues not just in the fossil record, but potentially within our own genetic codes and behavioural patterns. Recent groundbreaking genetic studies have identified archaic hominin DNA sequences in modern human populations that don't match known Neanderthal or Denisovan genetic signatures. Some researchers enthusiastically speculate this mysterious genetic material might represent direct Homo erectus contributions to our genome through interbreeding events that occurred before our species fully diverged from other hominin lineages. If confirmed, this would mean that Homo erectus lives on not merely as an ancestral species, but as a direct genetic contributor to modern human diversity. Countless fundamental technologies and adaptations that essentially define human existence, ranging from mastering controlled fire usage to developing sophisticated stone tool craftsmanship, from achieving expanded geographical territories to establishing cooperative hunting systems, initially emerged or received significant development during Homo erectus's extended evolutionary dominance. In absolutely genuine terms, they established the essential groundwork for everything that would subsequently unfold in human evolutionary history. When we contemplate the extraordinary journey of Homo erectus spanning 2 million years of Earth's historical timeline, covering 3 entire continents and navigating countless environmental transformations, we gain invaluable perspective regarding our own species' remarkably brief existence. Modern Homo sapiens have existed for merely about 300,000 years, representing roughly 15% of Homo erectus's evolutionary tenure. Our global civilization featuring cities, agricultural systems, and digital technology represents less than 1% of that extended time span. The prolonged success of Homo erectus powerfully reminds us that evolutionary triumph isn't measured exclusively by technological complexity or cultural sophistication, but primarily by adaptability and resilience when confronting changing environmental conditions. Using this crucial measurement standard, Homo erectus ranks among the most successful mammals, not merely hominins, to ever inhabit our planet. Their remarkable story also compels us to fundamentally reconsider what we actually mean by the term human. Traditional narratives of human evolution frequently portray linear progression from primitive to advanced stages, with each emerging species representing improvement over previous versions. However, the developing picture from paleoanthropological research suggests something dramatically more complex and fascinating. A diverse family tree of human species, each possessing unique adaptations and capabilities, sometimes competing and sometimes interbreeding, all contributing to the rich tapestry of human evolutionary development. Homo erectus wasn't some failed evolutionary experiment or imperfect preliminary draft of humanity. They represented an extraordinarily successful species in their own evolutionary context, with adaptations perfectly suited to their specific time and position in evolutionary history. The fact that they eventually yielded to other human species, including our own, doesn't diminish their remarkable achievement in pioneering numerous traits and technologies we currently consider fundamentally human. In our contemporary world, where our own species confronts unprecedented environmental challenges, ranging from climate change to resource depletion, the story of Homo erectus provides both inspiration and cautionary lessons. Their remarkable adaptability enabled them to flourish across diverse environments for an almost unimaginable time span. However, ultimately, even they couldn't overcome the combined challenges of rapid climate change and competition from more technologically advanced species. As we reflect upon Homo erectus's legacy, perhaps their most profound contribution to human evolution wasn't any specific technology or adaptation, but rather their pioneering establishment of a revolutionary ecological niche that anthropologists call the human adaptive niche. This unique position within Earth's ecosystem involves utilizing cultural and technological innovations to buffer against environmental challenges, rather than relying exclusively on biological adaptations that typically require thousands of generations to evolve. Homo erectus became the first species to substantially expand this distinctly human approach to survival. While earlier hominins demonstrated glimpses of cultural adaptation, Homo erectus elevated this strategy to unprecedented levels, crafting diverse tools, controlling fire, expanding into challenging environments, and developing social systems that allowed knowledge accumulation and transmission across generations. This fundamental shift dramatically altered human evolutionary trajectories. Natural selection began operating not just on physical traits, but increasingly on cognitive and social capabilities that enhanced cultural innovation and transmission processes. The result created a feedback loop between biological and cultural evolution that would eventually produce our own species with its unprecedented capacity for symbolic thought, complex language, and technological innovation. Recent excavations at Ethiopian sites have uncovered evidence that challenges traditional views of Homo erectus capabilities. Stone tools discovered at Gona demonstrate craftsmanship levels previously thought beyond their abilities. The precisely shaped implements reveal careful raw material selection and sophisticated knapping techniques requiring not just manual dexterity, but also advanced planning and spatial reasoning capabilities. What's particularly striking about these discoveries involves their age. Dating to approximately 1.6 million years ago, they demonstrate that Homo erectus achieved this technological sophistication level much earlier than previously thought. This pushes back the timeline for advanced cognition in human evolution and suggests that Homo erectus mental capabilities have been systematically underestimated by researchers. The geographical distribution of these advanced tools also reveals crucial information about Homo erectus societies. Similar technological traditions have been discovered across widely separated regions, suggesting sophisticated cultural transmission mechanisms that allowed innovations to spread between different Homo erectus groups. This hints at social networks and intergroup contact that would have facilitated not just technological sharing, but potentially also mate exchange, resource information, and other crucial survival knowledge. Another overlooked dimension of Homo erectus' existence involves their relationships with other species. Beyond hunting and avoiding predators, emerging evidence suggests Homo erectus may have engaged in proto-domestication forms, representing the beginnings of complex relationships between humans and other species that would later transform into full domestication. At several Homo erectus sites, archaeologists have discovered unusual concentrations of certain animal species that don't match natural accumulation patterns. These concentrations might represent the earliest evidence of humans creating ecological niches that attracted particular animals, perhaps by clearing vegetation areas or creating water features that drew specific prey species. While this falls considerably short of intentional breeding programs characterizing true domestication, it represents initial steps toward human-to-some manipulation of other species' evolutionary trajectories, a process that would eventually transform wolves into dogs, wild grains into crops, and reshape Earth's biosphere in countless ways. The cognitive implications of such environmental manipulation prove significant. It demonstrates that Homo erectus possessed understanding of cause and effect relationships over extended time frames, recognizing that altering landscapes in specific ways would attract certain animals, potentially making hunting more predictable and efficient. This capacity for environmental engineering represents yet another way Homo erectus transcended earlier hominin species. Rather than simply adapting to their environment, they began the distinctly human practice of adapting environments to suit their needs, a strategy that would reach its culmination in modern human civilization but has its roots in these ancient pioneers' behavior. The question of consciousness in Homo erectus remains among the most fascinating and elusive aspects of their existence. While we cannot directly access any extinct species' subjective experience, the archaeological record provides tantalizing clues about their mental world. The planning level evident in their sophisticated tools suggests they possessed what psychologists call autonoetic consciousness, the ability to mentally project oneself into future scenarios and plan accordingly. This capacity for mental time travel represents a crucial cognitive leap beyond the primarily present-oriented consciousness of most non-human animals. Similarly, their care for injured group members indicates sophisticated empathy forms and perhaps even theory of mind, the ability to recognize that others possess mental states different from one's own. The long-term care evidenced by healed injuries in fossil specimens suggests they could understand others' suffering and were motivated to alleviate it, cognitive and emotional capacities we typically associate with advanced consciousness. Even more intriguing are hints of aesthetic sensitivity and potentially symbolic thought in their collection of colourful materials and possible artistic productions. These behaviours suggest Homo erectus may have experienced subjective states beyond mere survival calculations, perhaps even the beginnings of aesthetic appreciation, curiosity, and wonder that characterise human consciousness we recognise today. While their mental world was undoubtedly different from our own, lacking complex language scaffolding and accumulated cultural knowledge that shapes modern human consciousness, it would be mistaken to view Homo erectus as merely instinct-driven automatons. The archaeological evidence paints a picture of beings with rich subjective experiences, social bonds, accumulated knowledge, and perhaps even symbolic thought beginnings. As we continue unearthing new evidence and developing more sophisticated analytical techniques, our understanding of Homo erectus continues evolving. Recent methodological innovations have enabled researchers to extract new information types from long-studied fossils, revolutionizing our picture of these ancient humans. Advanced imaging techniques like micro-CT scanning have revealed internal bone structures, providing insights into growth patterns, diet and health conditions not visible from external examination alone. Isotope analysis of teeth has opened windows into seasonal migration patterns and dietary changes throughout individual lifespans. Ancient protein analysis has begun complementing DNA studies, offering molecular evidence from specimens too old for genetic material survival. These methodological advances have transformed Homo erectus from a relatively static, one-dimensional textbook species into a dynamic, diverse, and complex branch of the human family tree. We now recognize significant regional variations, evolutionary changes over time, and nuanced environmental adaptations that paint a far more sophisticated picture than earlier researcher generations could access, revealing the true complexity and remarkable success of humanity's most enduring ancestors. Looking toward the future, revolutionary emerging technologies promise to dramatically transform our understanding even further. Breakthrough improvements in ancient DNA recovery techniques may eventually enable genetic material extraction from Homo erectus fossils despite their considerable age and frequently challenging preservation circumstances. This would deliver absolutely unprecedented insights into their evolutionary relationships, potential interbreeding events with other hominin species, and specific genetic adaptations developed for different environmental conditions. Meanwhile, agent-based modeling systems and other sophisticated computational approaches enable researchers to rigorously test hypotheses about Homo erectus social organizational structures, migration movement patterns, and complex ecological relationships that couldn't be directly examined through archaeological evidence alone. These innovative approaches, combining traditional archaeological methods with cutting-edge technology and advanced computational techniques, represent the exciting future direction of paleoanthropological research. What crucial lessons can we extract from the Homo erectus narrative that might inform our understanding of our own species' future trajectory? Perhaps the most sobering realization involves recognizing that even extraordinary evolutionary success doesn't guarantee indefinite survival prospects. After flourishing for 2 million years, representing a time span that completely dwarfs our own species' existence, Homo erectus eventually vanished entirely, unable to successfully adapt to the combined pressures of dramatic climate change and intense species competition. This discovery offers a powerfully sobering reminder about vulnerability, even for highly adaptable species. Our own global civilization currently confronts unprecedented challenges, including climate change, resource depletion, and accelerating biodiversity loss. The fossil record starkly reminds us that no species, regardless of their previous success, receives guaranteed continued existence when environmental conditions undergo dramatic transformations, yet the Homo erectus story simultaneously offers genuine hope and inspiration. Their remarkable adaptability enabled them to pioneer survival strategies that eventually led to our own species' emergence. They convincingly demonstrated the tremendous power of cultural innovation, social cooperation, and technological development to overcome severe environmental challenges, precisely the same strategies that might help us successfully navigate the challenges confronting our own time. The crucial difference involves the time frame of change occurring today. Homo erectus faced environmental shifts that unfolded gradually over thousands of years, providing adequate time for both cultural and biological adaptation processes. Today's anthropogenic climate change occurs at a pace completely unprecedented in human evolutionary history, compressing into mere decades changes that would normally require millennia to unfold. This dramatic temporal compression demands levels of foresight, global cooperation, and technological innovation beyond anything our evolutionary history has adequately prepared us to handle. Yet the fundamental seeds of these essential capacities were originally planted by Homo erectus when they first expanded the human adaptive niche to include cultural and technological buffers against environmental change. In this profound sense, we owe our potential for overcoming today's monumental challenges to innovations originally pioneered by these ancient relatives almost 2 million years ago. Their enduring legacy lives on not merely in our physiology and possibly our genetic codes, but fundamentally in the distinctly human strategy of utilizing cultural and technological innovation to transcend biological limitations. As we conclude this comprehensive exploration of Homo erectus, we return to contemplating the absolutely remarkable time span of their existence. For approximately 2 million years, representing a period so astronomically vast it challenges our mental comprehension, these extraordinary beings walked our planet. They witnessed countless generations passing, multiple ice ages cycling, drastically changing landscapes, transforming and the rise and fall of innumerable animal species throughout their extended reign. They successfully spread across 3 entire continents, masterfully adapted to environments ranging from dense tropical forests to challenging high-altitude plateaus, and pioneered revolutionary technologies that fundamentally transform the human evolutionary trajectory forever. Their incredible story isn't merely a footnote in human evolutionary history or some primitive prelude to our own species' development. It represents the most triumphantly successful chapter in all of human evolutionary history, serving as a powerful testament to the remarkable adaptability, extraordinary resilience, and pioneering innovativeness of our ancient relatives. In studying Homo erectus comprehensively, we gain invaluable perspective not just regarding human origins, but concerning what it fundamentally means to be successfully human in evolutionary terms. The genuine legacy of Homo erectus extends far beyond the fossils and artifacts they left behind for us to discover, encompassing the fundamental human capacities they originally pioneered, including technological innovation, social cooperation, environmental adaptability, and the cultural transmission of accumulated knowledge. These essential capacities, refined and elaborated through subsequent human evolutionary processes, remain absolutely central to what defines humanity today. Therefore, the next time you control fire to cook a nutritious meal, utilize a tool to solve a challenging problem, adapt your behavior to accommodate a changing environment, or share valuable knowledge with others, remember that you're actively drawing upon capacities originally pioneered by Homo erectus almost 2 million years ago. Their groundbreaking evolutionary innovations continue echoing through time, permanently connecting us to our ancient past while simultaneously shaping our ongoing human journey into an uncertain but promising future.